Hi, my name is Mel, and the following presentation and video will explore the journey from analogue to digital data transmission, emphasizing the fundamental concepts of signals, conversion processes, and the critical role that electricity plays in computing systems. So we'll cover the basic fundamentals of data and signals, explore analog and digital signals, examine conversion techniques between these forms, analyze key components involved, discuss how electricity supports computing, and explore data transmission methods and look into the challenges and future trends. The following section introduces the basic concepts of data in computing, differences between analog and digital signals, and the reasons for converting signals between these two forms. Data in computing refers to the information processed or stored by a computer system. It can represent text, numbers, images, or sounds, and is encoded in forms suitable for electronic processing. Analog signals are continuous and vary smoothly over time, while digital signals represent data as discrete levels, typically binary, like 0 or 1. Okay? Understanding the differences is key to data transmission and processing. So yeah, this is it's important in data transmission. Conversion is essential because real-world signals are often analog, but digital processing and storage provide advantages like accuracy, noise resistance, and ease of manipulation. In the following section, we explore examples, properties, and limitations in analog signals encountered in real environments. Common analog signals include sound waves, temperature reading, radio waves, all represented by continuously varying physical quantities. All right. Amplitude represents the signal strength. Frequency is how often the signal oscillates, and phase indicates signal timing relative to a reference, all vital for understanding analog signals. So phase is the timing shift of a signal relative to a reference point, and frequency is how often the analog signal completes cycle per second. Okay? Analog signals are susceptible to noise and distortion over distances, which can degrade the quality and reliability in data transmission. Okay, and this is definitely a problem. The following section focuses on how data is represented digitally and the benefits of digital signals over analog. Digital data is represented in binary form using two discrete states, commonly 0, which is normally sort of viewed as off, and 1 to mean on, to encode information for efficient processing and storage. Digital signals offer noise resistance, easier error detection and correction, and compatibility with modern computing systems, making them preferred for data transmission. Digital signals maintain integrity over long distances, or longer than analog anyway. So in the following section, we're going to explore processes of transforming analog signals into digital form for computer processing, analog to digital conversion, ADC. Sampling involves measuring the amplitude of an analog signal at regular levels, converting continuous data into discrete points. So this gives an accurate representation. Just looking at the video here, the slide. Quantization assigns sampled values to discrete levels, while encoding translates these levels into binary code for digital use. Devices like microphones convert sound waves to digital signals, and sensors digitize environmental data for computing applications. There's some real-world examples. The following section covers the process of converting digital data back into analog form for real-world applications, and this is called DAC, digital to analog conversion. DAC, or digital to analog conversion, is essential for output devices that require analog signals such as speakers and displays, enabling human interaction with digital data. The DAC process involves decoding digital data followed by reconstructing a continuous analog signal from discrete values. Audio systems convert digital music files into sound waves, and displays render digital images as analog light signals for viewing. Examining the hardware elements that facilitate analog to digital and digital to analog signal conversions. Interfaces serve as bridges between analog and digital components, enabling communication and signal exchange. Okay, so there's interfaces that do help interchange this. Transducers convert physical phenomena into electrical signals or vice versa, playing a critical role in data acquisition and output. Okay? These components manage signal conversion, processing, and control, forming the computational core of many conversion systems. Understanding how electric currents supports data representation and processing in computing devices. Computers use varying electric current levels to encode binary data, enabling logical operations and information storage. Distinct voltage thresholds represent binary zeros and ones, ensuring reliable interpretation of digital signals within circuits. Computers rely on stable power sources and efficient energy management to maintain performance and prevent data loss. Exploring how data moves internally through buses, interconnects, and the importance of timing for synchronization. So buses are the communication pathways carrying data between components, enabling coordinated operation of computer parts. Serial sends data bit by bit sequentially, while parallel transmits multiple bits simultaneously, each with trade-offs in speed and complexity. Timing mechanisms ensure data signals are transmitted and received accurately, preventing errors and maintaining system stability. The following section covers communication methods between computers and external devices over wired and wireless channels. Wired connections like Ethernet, optical fiber, and USB provide reliable high-speed data transfer between devices over physical cables. Wireless technologies enable flexible, cable-free data exchange, although they face challenges like interference and range limitations. Signals often require conversion to match the characteristic of the transmission medium, ensuring effective communication. So that could be for Ethernet or fibre or wireless or whatever. Concluding with the current challenges in data transmission and emerging technologies shaping the future of analog and digital integration. Signal loss and distortion affect data quality. Error correction techniques help detect and fix transmission errors to maintain integrity. Advancement like optical fibers and quantum computing offer promising improvements in speed, security, and capacity of data transmission. Continued innovation aims to blend analog and digital systems more seamlessly, enhancing computer capabilities and user experience. So look, in conclusion, the transition from analog to digital data transmission and the vital role of electricity provides insight into modern computing's foundation and future developments. Thank you for your time.